The next function is searching. Searching nothing but traversal, both are same. And whatever traversal techniques are there for binary tree, so the same traversal techniques will be applied for the binary search tree also. No change in that one. So now let us see searching. How do we search for an element in a binary search tree? How do we search for an element in a binary search tree? So we know that in a binary search tree, root node is always larger than the left subtree, and root node is always smaller than the right subtree. This is the property which is known to us. From the properties of binary search tree. Right? Say for example, if we have 100 as a root node here, so this must be 50 and 200. So this is what is simple binary search tree. I'll extend it with two more nodes, 50 and 60, and this is what is 150 and 250. This is one binary search tree. This is what is an binary search tree. Why? Because it is satisfying all the properties of BST or binary search tree. Root node is always larger than the left subtree. In other words, the nodes which are coming at the left side of the root node are smaller than the root node. The nodes which are coming to the right side of the root node are larger than the root. That is what is binary search tree. And whenever, how do we search for an element? So, searching in a binary search tree. Searching for a given element in a binary search tree. Say any key is given to you for searching. You will be given some key number. Say I'll say 150. So what is the logic that you follow? So the logic here is first we compare key with the root node. Compare key with the root node. Only three possibilities. Either key is equal to root node, or key is larger than the root node, or key is smaller than the root node. So larger than the root node, we have to search at the right side of the root node. That is understood. Why? Because if the element is, all the elements which are larger than the root node are lying towards right side. So that is understood. That is well known fact about binary search tree. So what we do here is compare key with the root node. If the key is larger than the root node, go to right subtree and start once again the search. Then this becomes the root node. Now from wherever you are present, compare that key element with that particular node. Now in this case, the key element is smaller than the root node. In this case, key element 150 is smaller than the root node 200 or the node 200. In this case, it is understood that we have to go towards left side. Now this becomes the new root node, or during the traversal, the pointer is pointing to this node now. Right? Now whenever you are present at the node, repeat the same procedure. What is that? Compare the key element with the root node or the node where you are present. Now key element is 150, node is also 150, and search is successful. After doing all these comparisons, say assume for example if this is 160, we have come to this location and there is no left subtree and there is no right subtree. In this case, what we do, we say that search is not successful. In this case, we say that search is not successful. Whereas in this case, the search is successful because 150 is present here. That is the simple logic for searching an item in a binary search tree. So what we do, check for the empty tree, because before you search for the elements in a binary search tree, you should make sure that binary search tree is existing. Because if tree itself is not there, we cannot search for the elements. If tree itself is not there, we cannot search for the elements. So that's why first make sure that binary search tree is present. If tree is empty, we simply return saying that we cannot perform the search. That means if root is null, simply return null, saying that there is no binary search tree and we cannot search for the elements in the binary search tree. That is the simple thing that we do first. And step 2, what we do in step 2, search for the node in left subtree and right subtree. So based on the element comparison, just what I explained. Search for the element in the left subtree and right subtree both. And when current becomes null, we say that key is not present. That means while searching, if we find that key is not present after searching the whole screen, then we say that search is not successful. Then we say that search is not successful. Alright, the same theoretical concept is written in terms of the code now. So what we are trying to do is we are trying to perform the search where we are trying to perform search of this particular item. It can be anything. Say for example, just now we observed 150. So I want to search for this item where in this tree pointed by this root node. In this tree pointed by this particular root node. So when you call the function, we take the appropriate pointer called current, which will always point to the current node, and we check for the empty condition of the tree. That is, if root is equal to null, that means tree is not existing. If tree is not there, we cannot search for the elements, and simply we return null value. Then say if there is something like symbolically, I will try to draw. So root is always pointing here. Then current is also pointing to that node. Why? Because we are not going to change the root node for traversal purpose. We will always change the value of the current node for the traversal purpose. We will always change the value of the current node for traversal purpose. So that's why current is made to point to the root node. Wherever root is pointing to the same node, current is pointing now. Right now, while till current becomes null, because only two possibilities are there for you. Either you have to traverse towards left subtree or you have to traverse towards right subtree. Only these are the two possibilities available. So till current becomes null, because when you go on traversing towards left side, you may reach null at some point of time. Whenever you are traveling towards right subtree also, you may reach null. So till we reach null, what we have to do? We have to search for the item. So whenever you are searching, it is possible that the first node itself can be the key item which we are finding. First node can be the key item. That's why check the condition of whether item is it equal to current pointer info. That means current pointer info means this element. Whether the first element itself, whether the first node itself is the item which we are finding. In this case, current saying that the element is found in this location itself. The very first location itself is having the element which we are searching. Having the element which we are searching. Right? That is what is first condition. Another possibility is, like as I said just now, the key element can be smaller than the root node or key element can be larger than the root node. Those are the other two possibilities. So those are the other two possibilities. That is, if whether the item to be searched is larger than the root node or larger than the current node. That is, if item is less than current pointer info. In that case, it is understood that our item to be searched is lying at the left subtree. At any cost, you should search at the left side. At any cost, you should search at the left side. That's why what we are doing, we are descending towards left side. We are descending towards left side. How? With this particular statement. Make current to point to left subtree of the current node. That is current equal to current pointer left link. Take the current and make it to point to left subtree. So instead of this place, what I will do? Okay. Instead of this place, this is the case. Current will point to the left subtree. That means current will descend down towards left subtree. Why? Because this condition is satisfied. Item which we are searching is smaller than the current node. If it is smaller, it is understood that we have to search towards left subtree. Right? Else, if it is larger, third possibility, only three possibilities, either it is equal, smaller or larger. If it is larger, instead of descending down towards left side, now we will descend down towards right side. That is the third possibility. That is current equal to current pointer R link. So this diagram may help you to better understand once again, right? Based on this, we compare always with the root node key element. If the element to be searched is smaller than the root node, we go towards left subtree. If the element to be searched is larger than the root node, we go towards right subtree. And we go on performing the same comparison again and again till we find the element, or at the end, the element may not be found and the search is unsuccessful. And we say that element is not present. We say that element is not present. So when that is indicated element is not present, after doing all this till you get null value, we have traversed everywhere and we have not found the element, and finally we are going to return null value. So returning null, what it indicates, the element to be searched is not found. We don't have the element to be searched. That is what is the indication at the end. So this was the function for searching for an element, and the same code can be written by using recursion. That is recursive procedure. Let's compare the root with the null value. If that is the case, simply return root, saying that the element, there is no tree itself and we cannot search the element. Else compare the item with the root. That means the first node itself is the item. In that case, we return the root. The same iterative procedure, the above iterative procedure is written in the form of recursion. Compare the item with the root pointer information. That is whether the item which we are searching is smaller than the root pointer information. Whether the item we are searching is smaller than the root pointer information. In that case, we have to go towards left subtree. That's what we are calling the search function once again, the same function once again, but passing different parameters. The item which you are searching plus go towards left subtree. Why I have to go root pointer left link? Because the item to be searched is smaller than the root node. If it is smaller, we have to go towards left subtree. Otherwise, you have to go towards right subtree. That is what is all the search function. Once again, by passing the same key item which you are searching, but descending down towards right subtree. Descending down towards right subtree. So this was the procedure finding or searching for an element in a binary search tree. So this was the procedure for finding or searching for an element in a binary search tree.